We left off with the Taylor formula. Now, one thing I need you to know is that these things are an extension of the concept of tangent line. And thus, I and other people I know have called them tangent polynomials. However, that's not what they're called. That's what they are. They are an extension of the idea of tangent line. And I think it's extremely important that you see that connection. And the textbooks don't even mention it. And so I try to make sure to clarify that for people, that Taylor series are really just an extension of a tangent line into what could be called a tangent polynomial. But what they say is that this is a formula for a Taylor series centered at x equals a, where a is the x-coordinate of the, quote, point of tangency. But you're going to see why they use the phrase centered as we look at the examples today. So this is the formula we came up with, and this is the formula we are about to use. So I want to also clarify the directions of your homework and what I expect you to do and what you don't have to do, because we are dealing with online and that creates some extra problems. So I want you to know that with these homework problems, part A is the main piece. And that's actually all that when these came from textbook problems, but I morphed them. Originally, this was the main piece of what it said to do. What I want you to do on top of that is, after you find the first four non-zero terms, and I'll explain what that means. After you do that, I want you to, for the sake of your understanding of what's going on, I want you to, using Desmos or a graphing calculator, graph the function that you were given and then the Taylor polynomial that you find in part A, and take a screenshot. If you're not able to upload a screenshot, I do not want you to sit there and draw this out. That's a waste of your time. So if you cannot, I will not penalize you. I'm not going to expect to see a picture. I will assume, if you don't have a picture, that you just weren't able to upload a screenshot, or that was too difficult to do, and that you did look at the picture. Do you get what I'm saying? Okay. Now, understand part C is an opinion, which means I'm not going to throw this at you on a test. This is presented as an opinion because I want you to begin to see something that is going to be formalized later. And a good approximation is dependent upon the actual application and what good is. Approximations being, quote, good really has to do with a real world situation. So you're just kind of looking at the graph and saying what your opinion of is, what x interval does this look like a good approximation? And it's mostly just I want you to see something, and I'm going to talk about that as I go through an example. Part D, I don't want you to spend too much time. Do not spend too much time on this. If you have 3 or 4 academic classes right now, or if you are working at the same time, some of you don't have the time. And I don't want you to spend too much time. That's why I say see how many you can figure out within a reasonable amount of time and then let it go. So what does that mean? That means on your homework answers, I'm very much expecting to see A. And then a quick answer for C. Anything else you have is bonus. and I'm not going to penalize you for not having those things. It's really valuable to come up with these general formulas, but I know that there's a huge range in how much time each one of you is going to need to spend to get to that formula. And that's why I want to throw out there, don't spend too much time on it. Put in some time and then let it go. That makes sense? Okay. Now, here we go. We are going to use the Taylor formula that we were just looking at. So I'm going to write that down. And I want you to write it down partly to get used to it because of how important this formula is. So sigma from n equals 0 to infinity, but we're not going to go that far. And it is the nth derivative at the center a divided by n factorial times x minus a to the n power. And what I'm going to do is I'm going to first talk you through this sigma formula. And that's why I'm going to talk you through the sigma formula. I'm going to answer that question as I do this. So right now, I'm not actually doing the homework problem yet. I just want to make sure this formula makes sense to you. So with sigma, you should remember that whatever it names as the variable, this integer is the first number you plug in. You get an answer. Then you add, and then you bump that integer up one, plug that into everywhere that the variable shows up in the formula, and then add that to plug in the next one until you reach whatever the final number is here. We're not going to reach infinity, though. I'm sorry to tell you that. When n is equal to 0, this formula is the 0th derivative at the center over 0 factorial times x minus a to the 0 power. What do all these mean? I'm going to start you off with this piece. If you have a 0 exponent, what number are you dealing with? The number 1. I'm not going to get into the exception of the rule at this moment. I'm just going to put down that that's 1 times. Then I'm going to move to what does the 0th derivative mean? That just means when you've taken the derivative 0 times. So what does that mean? The function. You got it. Just the function at x equals a. So I'm going to put that down. Then 0 factorial, I'm not going to get into it right now because it's a whole nother ball game of explanation. There are videos on it. Some are good, some are helpful. Sometimes even when people see it, they don't like it. 0 factorial is 1 because the math forces it to be so. And I'm going to leave it at because the math forces it to be, because if I start into it, it's going to take like time that I don't have. So I will say look up why is 0 factorial equal to 1. So what that means is when n is 0, you are simply getting f of a. If you understand that that is what you're getting every time, you're going to save your time with this formula. But I want to make sure you understand that this formula is in place for each term. You need to know that. When n is equal to 1, save your time as well. you have the first derivative at the center divided by 1 factorial times x minus a to the 1 power. How would you actually write that? Just first derivative at a times x minus a, where this is a number. This is a number. Then the formula really starts kicking in when you hit n equals 2. When you hit n equals 2, then you're really looking at, okay, second derivative over 2 factorial x minus a squared. And then n equals 3, third derivative at the center over 3 factorial x minus a cubed. And at that point, you should get the idea. So save your time, but understand that that formula is in play at all times. Now, we are going to do number 1. Come on. All right. I'll click, and then you will agree to move. There. See how easy that was? So this is the problem we're doing together. We're doing part A right now, and I'm going to talk you through an organized way to get through this problem. I'm going to move my screen over so it's 1 over x, center is negative 3. All right. The big thing is you need 2 columns. However, you might want to first kind of say, here are my n values. They are 0, 1, 2, 3. Now, the directions ask you for the first 4 non-zero terms. That means at a minimum, you need 4 lines. Then you're going to write the nth derivative of the function, because you're going to have to sit there and take the derivatives. You may want to simplify it. It's up to you. And then you need to take that derivative order and plug in the center. We began with the function 1 over x, and that is the 0th derivative. I'm going to write it as x to the negative 1 to make the derivative easier to go through. So here we go. Derive away. Negative x to the negative 2. Differentiate again, and you are going to get positive 2x to the negative 3. Differentiate again, negative 6x to the negative 4. Now, depending on how you function, you may want to rewrite these, but you don't have to. I'm going to rewrite them with positive exponents because I will warn you, when people mess up on these, it's because they don't properly recognize that negative exponent as to where it's actually located. People just mess up on those really easily. So I'm going to focus on the more simplified version and plug negative 3 in. So now I'm going to specifically say that my a is negative 3. And let's see what we get. For 1 over x, that's going to be negative 1/3. And I just realized I didn't write correctly. There we go. Forgot my negative. That negative is that negative, and then the negative exponent. So I have negative 1 over, if I'm squaring negative 3, I get positive 9. Next, I have positive 2 over x cubed. Positive 2 over. When I cube a negative number, the negative stays. And then 3 cubed is 27. And then the next one is negative 6 over x to the fourth. Negative 3 to the fourth power is positive. 3 to the fourth power is 81. And they each keep coming out negative. How cool is that? Was that kind of fun that that happened? And that does happen quite a bit. Now, you're going to want to write the simplified version. So maybe you want to simplify as you are moving along. Maybe you don't. I'll simplify right now. I can divide by 3. And sometimes this does happen where a couple of them in a row are the same answer, negative 2 over 27. It's going to be different on the next one. Shouldn't we put 2 forces? So the reason I didn't go to n equals 4 is because the n equals 0 term is counting as one of those non-zero terms. However, we're going to see on the second example that I do with you that if any of these come out as 0, then you have to go and do another one. But otherwise, that's enough to answer part A with finding the first 4 non-zero terms. Trying to get that off. Okay, now we're going to the formula. You do all of this work before you even start writing your polynomial. Because now I'm going to move to the Taylor formula. The Taylor formula says nth derivative at a over n factorial times x minus the center to the n power, starting at n equals 0. And in this situation, I only need to go to n equals 3, and that will go through 4 terms if 0 is my starting point. If you want to save time, be aware that when n is 0, it is purely just f of negative 3 alone. That will save you a lot of time if you recognize that the n equals 0 is just the function's y value. And that is negative 1/3. You have your first non-zero term. Sigma says add, and it says add 1 to the starting n. Now we're at 1. In this formula, after simplifying, that turns into the first derivative at negative 3 multiplied by, now the center is negative 3. That's my a. So in this situation, it's x minus negative 3 to the 1 power. I know that f prime of negative 3 is negative 1/9. And then sigma says, go up 1 integer. Now it's n equals 2. Now I'm finding the second derivative at the center divided by n factorial, which is 2, n is 2 right now, times x minus the center is negative 3, and right now n is equal to 2. My second derivative at negative 3 is negative 2 over 27, and I'm dividing that by 2 factorial, which is 2. And then I can simplify. Dink, dink. And then I'm going to start writing this. And I now have 3 non-zero terms. 1, 2, 3. To get the 4th non-zero term, I make sigma go up 1 more to 3. I need the 3rd derivative at the center over 3 factorial times x minus the center to the n equals 3 power. The 3rd derivative at the center is negative 2 over 27. 3 factorial is 6. And then I want to simplify. As I simplify, I'm going to look at divide by 2, divide by 2, and then 1 over 27 divided by 3 will become, and my negative sign, 1 over 81. This is the answer to part A. And that is the big thing that you are doing as you are learning about the Taylor formula. And now I want to talk you through what I want you to look at about this. Instead of just writing it down, you've got an answer, and it's so far just how to use a formula. Let's bring some meaning to it by seeing what this did. So I've got Desmos ready, and hold on, close your eyes. I'm kind of joking when I say that because you can't really. Anyway. Okay, I need to give me a second. I forgot to re-prep after the previous class, so I'm going to open that up. There we go. All right. What I have here is in blue, you can see the graph 1 over x. In red, I have the polynomial that we just found, all nice and typed out. And now I want you to look. Okay, I am in projector mode. Take a good look. Opinion is now part C. Just take a screenshot of this if you're able to, put it in your homework. If you're not able to, I will assume that you looked at it. Now, the center of the polynomial was negative 3. Here's negative 3. Do you see visually why they call it the center? And now I want you to, with your own opinion, because it's going to differ, what is a good approximation requires an actual application to know what's good enough. You're just visually looking at this, and I'm wanting you to visually see that this graph looks like a good approximation for an interval of x. What would you put down? And the question was, do we simplify our answer? Simplify the polynomial. Simplify the coefficients of that polynomial. Okay? Yep, that's reasonable. Now, you might see, did it stop my settings? I think it stopped my settings. Okay. So center -3. If you go 1 unit to the right, it looks really good. You go 1 unit to the left of the center, it looks really good. But as you go from there, you're going to vary on whether you think it's a good approximation or not. Does there reach a point where you feel like it's definitely horrible, should not be used? Now, whatever interval you have, you're going to write that down. And then you're just going to move on to part D, and I'm going to talk about D later. First, I want us to investigate and discuss what we see here, which is not part of the homework assignment. But if you can think about these things, that will help you. I would put it as open brackets, and I'll explain more as we go along why. I'm recording, right? Yes. Okay. The next thing I'm going to do is I'm going to take out the spaces that I put in here because I wanted you to not see the formula. Which reminds me that perhaps what I should first do is talk to you about how to come up with the formula before I show it to you. So I'll do that, and then I'm going to come back to the graph and discuss it. If you're trying to come up with a general formula, realize that, okay, really? Really? You're going to play this game with me? Okay. I don't understand. Why is this being so cruel to me right now? Okay, let's try it again. There we go. Of the formula, the nth derivative at the center is the only thing that creates a different formula for a different function at a different center. So ultimately, your focus is on this last column. But if you're not able to see the pattern in that last column, take a look at the pattern the derivatives themselves give you. When I look at the final column, I can see definitely that these are going to just continue to be negative numbers every single time. Then let's think about what's the fourth derivative? You could say the fourth derivative is 24x to the -5, but you could also see the numerator as what's happening. Right here, I had just a 2. The 6 came from 2 times 3. The 24 is coming from 2 times 3 times 4. That can help you to see where this numerator is coming from. If n is equal to 4 and I don't simplify, then knowing that negative is just going to be there every time, 4 factorial is my numerator if n is equal to 4. For a general n, that's going to be n factorial for my numerator. And then look at the denominator. We dealt with the negative issue of the center already. With that aside, you want to see that the denominators were 3 to the 1, 3 squared, 3 cubed, 3 to the 4th, and now 3 to the 5th. So if I reach generic n, the nth derivative, then the denominator would be 3 to what power? N plus 1. If you figure out the formula for the nth derivative at the center, you can literally plop it in and simplify. So I'm taking the formula of Taylor's series, and I'm not going to write the sigma, I'm just going to write the formula part. I'm going to wait and do the outline of divided by n factorial x minus the center to the n power. And then separately, I am going to plug in this formula and simplify. And when I simplify, the n factorials cancel each other out. And I now have a general formula. Now realize that for some of you, you are going to be able to look at the pattern that's happening here. And from looking at just that pattern, come up with this formula. You might find that some of these, it's easy to just kind of go straight from the pattern you see coming up to here. Others are going to be more complicated. But that just gives you some ideas of how you can come up with this general formula. And I want you to know that when the AP test asks you for a general term, this is very, very important for the AP exam. General, general, there we go. General term means the formula that you would see in sigma. So it's just the formula alone. But understand that when you write the formula inside sigma without the sigma, you're not telling it what the starting n is, which means that your formula could look different from someone else's formula by being, say, maybe the term before the one you have here or the term after the one you have here. What does that mean? If this is the nth term, another general formula would be the n minus 1th term. That is also a general formula. The n plus 1th term is another form of a general term. If I want the n minus 1th term, I literally put into all of the n's n minus 1. If I want the n plus 1th term, then I replace all the n's with n plus 1's. So be aware that your general formula could look different from someone else's general formula and still be representing the same formula. Now, that is all you're expected to do for the homework problem for number 1. See if you can come up with the formula. Part D, done. But now I want us to go back to this Desmos, and I have prepared for you a general formula. Let me move that up. Okay. I'm going to take away the polynomial. And let's see. Okay, there's enough. You can see that you have the function 1 over x. And if I'm only going from 0 to 1 on my sigma, I'm looking at the tangent line. So I'm going to show you there's the tangent line. When I push play, this thing is going to play really quickly. And I've got to tell you, it's amazing it goes this quick. Here it goes. Once you get past about 20, it starts having a little bit of a difficult time. And if I go past 30, I start getting Desmos is broken. And you see weird things all over the place until it figures it out. But this is quite a few terms of the polynomial. And I want us to talk about what is here. Desmos is still thinking. There it goes. 1 over x has a vertical asymptote at 0. If a polynomial is trying to mimic a function that has a vertical asymptote, it's only going to be able to approach that asymptote, and it's done. It can't go over to the other side of the asymptote. And if I didn't answer the question I see in chat, that was a general rule for that particular function at that particular center. But do you see something interesting? The center of the polynomial was 3. The vertical asymptote is 3 units away from that center to the right. If I go back to the center and I look 3 units to the left, what do you find happens 3 units to the left? Yeah. Are you starting to see a little bit more why they call it the center? Because the polynomial is only going to be a good representation for a particular distance from the center. You might say for a particular radius from the center. Yeah. Yep. It gives you a nice little margin of error. And this is going to continue happening. Anytime you have a function with a vertical asymptote, whatever the distance your center is from that vertical asymptote, the polynomial is only going to be good for that same distance on the other side. And it's intriguing to think about. So something to think about. Why does that work? Very exciting, good stuff. But what you're seeing here is we are heading to something that is very important. We need to know what values of x we can actually use the polynomial with, and what values of x we cannot use the polynomial with. That's extremely important. Right now, you're just getting a look at it, but I'm taking you straight into the Taylor formula because that's the what this is all about. That's what this is all for. Now, I'm going to go over one more example with you. And this time I'm going to introduce you to a vocabulary word. Maclaurin. Ooh, did that sound Scottish? Because it's supposed to. It didn't? Okay, then you need to look up a pronunciation for it if you want to say it right. We usually just say Maclaurin, but it's Maclaurin, however that is supposed to sound. Anyway, you are expected to know that when they use the phrase Maclaurin series, they are meaning a Taylor centered at 0. Other than that, these are all the same directions as before. You just have to know that with Maclaurin series, you aren't given a center because you know that means the center is 0 automatically. We're going to do number 4 together. And so the first thing we do is we have to find all of the derivatives with respect to x, and then find those derivatives at the center, and the center is 0. When we start using the Taylor formula in the Maclaurin version, the Maclaurin is nth derivative at 0 specifically over n factorial. And instead of writing x minus a to the n, let's not bother and just write x to the n. So this is specifically the Maclaurin formula. And that's what we are going to be using. But we set up this table to figure out this particular portion of the formula. If I'm going to have 4 non-zero terms, then I'm going to at least have to find for n equals 0, 1, 2, and 3 to get 4 things. The function is natural log of 1 plus x. And I'm just going to go deriving. Deriving we will go, deriving we will go. Okay, yep. Derivative. 1 over bleh times the derivative of 1 plus x, which is 1. I'm going to rewrite this as 1 plus x to the negative 1 because the derivative will be far nicer to me if I do that. Then, from that formula, taking the derivative, exponent is negative 1, so negative 1 bleh to the negative 2. Chain rule says shove in baby times derivative of baby is 1. There we go. Derivative again, negative 1 times negative 2, bleh to the negative 3, times the derivative of 1 plus x, which is 1. And now let's start plugging in 0. On the first line, when I plug in 0, I get the natural log of 1. What does the natural log of 1 happen to be? 0. You know what that means? That means I need to find another derivative. Some people just find several derivatives so they don't have to bother going back. Because once you go back, you've got to remember where you were at, and you were in kind of a zone of a pattern. So now 2 times -3 gives me -6. Bleh. Subtract 1 from the exponent times the derivative of 1 plus x is times 1. So there we go. And then I'm going to look at the formula without having the negative exponent. People tend to mess up less when they look at it in that format. When I plug in 0, I'm getting the number 1. Woo! A lot of work just to get 1. And then I'm going to real quick write this with a positive exponent so that I don't accidentally misinterpret what's there. And then I look at it and go, okay, that's -1. And I think at this point, I might be seeing that each time I plug in 0 to x, all I'm getting is, those are all 1. So when I plug in 0, my third derivative is 2. My fourth derivative is -6. And now it's time to create the polynomial based on the Maclaurin formula. And you do want to save your time. When n is equal to 0, all you're getting is the actual function value at the center. When n is equal to 1, all you're getting is the first derivative at the center divided by 1 factorial, doesn't need to be written, times x minus a to the 1 power. And if my center is 0, then all it is the first derivative at 0 times x. The formula kicks in a bit more once we hit 2, where we can actually see something different. Second derivative at the center over 2 factorial times x squared. Third derivative at the center over 3 factorial times x cubed. And because we got 0 for f of 0, that's just going to give me, I'm not even going to bother writing that term. It's a 0 term. And I'm going to need to move to n equals 4. I want to emphasize to you that derivatives, when they hit the fourth derivative, you stop doing the prime symbols and you have to write parentheses, the order number in like a superscript. And 10 minutes are left. All I have to do now is fill in those derivatives with the numbers that were found. So here we go. Starting here, since the other one was 0, 1 times x. Then second derivative at 0 is -1. 2 factorial is 2. Then the third derivative at 0 is 2 over 3 factorial, which is 6. The fourth derivative is -6. And I just realized that I wrote that wrong. There we go. That should have been a 4 factorial down there to follow. Yeah, you guys were trying to tell me, and I ignored the chat. And then 4 factorial is 24. And then you can just simplify it. And I'm going to grab Desmos again. I'm going to leave that up. You can simplify it on your own, and I'm going to prep my Desmos. Okay. I'm bringing it back over. Isn't the positive 2 supposed to be a negative? For this one, the two negatives this one's actually going to go back and forth between positives and negatives, which fortunately I've got time to go over that, which is why I didn't explain 0 factorial. So here we go. This is what you are going to see when you graph the polynomial that has the first 4 non-zero terms and the function. Remember that the center was 0. And you know that the natural log function has a vertical asymptote at the x that makes the interior 0. That x is -1. Now, this is only the first 4 non-zero terms. So it's not going to have as good of accuracy as a 30-degree polynomial. But you can see that it definitely is not going to work past this asymptote because nothing exists over there. That asymptote is horizontally 1 unit to the left of the center. That means this is only going to be good for up to 1 unit to the right. And you can start to see that it's just going, no, at x equals 1. I'm going to show you what it looks like with a higher degree polynomial, but you're just going to say what you think is a good x interval. Maybe you say it's only good from -1/2 to +1/2, or maybe you say from -1 to 1, but open interval. And now let's talk about, can I come up with the general term, which is part D. Okay. You want to really look at the pattern going on here and realize that 6 is coming from 2 times 3. Next, I'm going to have positive 2 times 3 times 4. Then I'm going to have negative 2 times 3 times 4 times 5. And then when I multiply that negative to the negative, it will go back to positive, but this time be 2 times 3 times 4 times 5 times 6. But what really matters is the formula in this final column. So you should notice that when you plug in 0, you just get what's in front of those parentheses. So when n is 5, I'm getting 4 factorial. When n is 6, I'm getting negative 5 factorial. For 7, I'm getting positive 6 factorial. Now, how do I make a formula go back and forth between positive and a negative and a positive and a negative? And you guys are seeing that with the exception of, is it negative or positive? Other than that, it's n minus 1 in parentheses factorial. If it's not in a parentheses, it's not part of the factorial. That's why these negatives And by the way, negative numbers in a factorial are very theoretical. You can look it up. There are mathematicians who have done videos on what that theoretically is. I'm not going to talk about it. I'm going to keep going on this. The positive or negative goes back and forth. My negatives are showing up every time I have an even n. So what kind of a form? Oh, yep. You got it. If the negatives had occurred when n was odd, then you would do -1 to the n power. Because it's even, you're either going to do n plus 1 or n minus 1, depending on what you want to use. It's up to you completely which one you feel like using. Because of the fact that I'm dealing with n minus 1 right here, I might want to use -1. But I can use +1. It does not matter at all which one I use. So when I bring that into the general formula, I have -1. I'll write n plus 1 because I like it better. I just do. N minus 1 factorial. That is the nth term, what is highlighted in yellow over here. Then I'm just going to bring this in and simplify. And do you see what's going to happen with these two? This is very important. N factorial means n times n minus 1 times n minus 2 times n minus 3 until we reach 1. N minus 1 down to reaching 1 is n minus 1 factorial. And that then gives me -1 to the n plus 1 divided by just n times x to the just n. And let me make sure you're clear that this can be +1 or -1. Doesn't matter. And that is a general formula. And now let's grab Desmos. Again, don't spend too much time trying to come up with a formula if you don't have the time. Okay, I'm going to bring this back to tangent line. I'm going to get rid of these. I put the spaces in so you couldn't see the formula when I brought it up. Oh, I wrote -1. Okay, doesn't matter. Here we go. Tangent line. I'm going to back out a little bit. Are you ready? I'm going to push play. Here we go. Whee! By the way, that was Desmos going, do you see? It's starting to have a hard time. I'm going to bring it over to 30. There you go. So you can also see that if the polynomial, if you end on an odd degree polynomial, you've got the opposite directions of your polynomial. If you end with an even degree polynomial, you've got the ends going same direction. But it continues to be that if I am only a horizontal distance of 1 away from the vertical asymptote of the function I'm mimicking, I can only mimic it for a horizontal distance of 1 in both directions. And you'll see that that polynomial just all of a sudden, right as it's getting close to 1, I mean, if you really zoom in, and if I put in a much higher degree polynomial, which would take Desmos quite a while, you would see this drop off even further in. Because if I bring it over to like here, you can see it might not look like it's dropping off as incredibly. It's when you get up to the higher degrees that you really see the sharp going, taken off. So is that pretty cool? Then let me repeat your homework. The only thing that I need to see is your polynomial, which is letter A for both of these, and your opinion on a good X interval. From there, if you have the time to come up with the formula, it's fun to try and play with it. If you're able to take a screenshot and add it to your homework, that would be fantastic for your own self to look back on. But I do not want you to waste time drawing.